So happy day everybody. This is Dr. Nivashini from Balaji Dental College doing my first year PG in the Department of Conservative Endodontics. So we are going to see about the mechanical properties of dental materials. Before going into the presentation, I would really like to tell you that go through your books before going for your exams, or if you need detailed knowledge on anything that is there, you will always have to read books. This is just a gist of knowledge that I'm going to share with you all. So, mechanical properties. It is a property of a material when it is linked to application of force. It describes how it will react to the physical force. These are all the mechanical properties that we are going to see in detail in the next few slides. Stress. Stress is nothing but force induced by or resisting an external force. Stress is equal to force per unit area. Stress is equal and opposite in direction to the load or external force. There are three types of stresses. First is tensile strength. Two sets of forces that are directed away from each other in a straight line, that is tensile stress. Compressive stress is two sets of forces that are directed towards each other. Shear stress is two forces that are directed parallel to each other. Strain. Strain can be defined as a change in length per unit length of the body when subjected to stress. Strain can either be plastic or elastic. Elastic strain is a strain that totally disappears once the external load that caused it is removed. Plastic strain is strain that permanently remains once the external load that caused it is removed. It occurs when the force applied to the atoms moves them so far from their equilibrium position that they do not return to it once the force is removed. Poisson's ratio. During axial loading and tension or compression, there is simultaneous axial and lateral strain under tensile loading as the material elongates in the direction of load. There is a reduction in cross section. Under compressive loading, there is an increase in cross section. Within the elastic range, the ratio of the lateral to the axial strain is called Poisson's ratio. Proportional limit. It is defined as the greatest stress that a material will sustain without deviation from the linear probability of stress to strain. Below the proportional limit, no permanent deformation occurs in the structure when the stress is removed. Structure will return to its original dimensions. Elastic limit. It is defined as the maximum stress that a material will withstand without permanent deformation. Also is defined as the greatest stress to which a material can be subjected such that it returns to its original dimensions when the force is released. The region of stress and strain curve before the proportional limit is called as elastic region. Yield strength. It is also known as yield stress or yield point. It is defined as the stress at which a material exhibits a specified limiting deviation from proportionality. It is a property that can be determined readily and is often used to describe the stress at which the material begins to function in a plastic manner. It defines the transition from elastic to plastic behavior. Modulus of elasticity. It describes the relative stiffness or rigidity of a material which is measured by the slope of the elastic region of the stress strain graph. It can be determined from stress strain graph by calculating the ratio of stress to strain. Elastic modulus E is equal to stress by strain. The interatomic or intermolecular forces of the material are responsible for the property of elasticity. The stronger the basic attraction forces, the greater the values of the elastic modulus and the more rigid or stiff the material. This property is generally independent of any heat treatment or mechanical treatment that a metal or alloy has received, but is dependent on the composition. It measures the elasticity of materials such as elastomers and other polymers have low values for elastic modulus, whereas many metals and ceramics have much higher values. Flexibility. It is defined as a flexural strain that occurs when the material is stressed to its proportional limit. Resilience. It is the resistance of a material to permanent deformation. It indicates the amount of energy that is necessary to deform the material to the proportional limit. It is measured as the area under the elastic portion of stress strain curve. It can also be defined as the amount of energy absorbed within a unit volume of a structure when it is stressed to its proportional limit. Ideally, the restorative materials should exhibit a moderately high elastic modulus and relatively low resilience. Impact strength. It is defined as the energy required to fracture a material under an impact force. The term impact is used to describe the reaction of a stationary object. The impact resistance of a material is determined from the total energy absorbed before the fracture when struck by a sudden blow. Some substances offer relatively little resistance to the shock, whereas the other of different composition may not fracture under the same impact. Permanent deformation. If a material is deformed by stress at a point above the proportional limit before fracture, the removal of applied force will reduce the stress to zero, but the strain does not return to its original dimension when the force is removed. It remains bent, stretched, compressed, or otherwise plastically deformed. In stress strain graph, the region between elastic limit is called as plastic region. Strength. It is the resistance to fracture. There are three types of strength, mm, just like stress. So it is tensile strength, maximum stress the structure will withstand before rupture. Compressive strength is the capacity of the material or structure to withstand loads tending to reduce size. Shear stress, the maximum stress that a structure can withstand before failure in the shear mode of loading. Flexural strength. It is obtained with a simple beam simply supported at each end with a load applied in the middle. Such a test is called a three-point bending test, and the maximum stress measured in the test is called flexural strength. This test is collective measurement of tensile, compressive, and shear stresses simultaneously. Fatigue. Fatigue is defined as a progressive fracture under repeated loading. Fatigue tests are performed by subjecting a specimen to alternating stress applications below the yield strength until fracture occurs. It is the stress that at which a material fails under repeated loading. Therefore, failure under repeated loading is dependent on the magnitude of the load and the number of loading repetitions. Toughness. It is defined as the amount of energy required to fracture a material. It is the measure of energy required to propagate critical flaws in the structure. Tough material is generally strong, although a strong material is not necessarily tough. Toughness is also known as the resistance of material to fracture. Brittleness. It is the relative inability of a material to sustain plastic deformation before fracture of the material occurs. Brittle material is not necessarily weak. Brittle materials are much weaker in tension than in compression, which contribute to failure of the materials. Ductility and malleability. Ductility represents the ability of the material to sustain a large permanent deformation under a tensile load before it fractures. The ability of a material to sustain considerable permanent deformation without rupture under compression is called as malleability. Hardness. It may be broadly defined as the resistance to permanent surface indentations or penetrations. It is the measure of resistance to plastic deformation and is measured as force per unit area of indentation. It is indicative of the case of finishing of structure and its resistance to in-service scratching. Some of the most common methods of testing the hardness of restorative materials are Brinell, Nu, Vickers, Rockwell, Barkol, and Share. All these tests have one common quality that each depends on penetration of small symmetrical shaped indenters into the surface of the material being tested. Conclusion. Mechanical properties are important in understanding and predicting a material's behavior under various conditions. Therefore, it is helpful in determination of clinical failures, whether they are caused by material deficiencies or human errors or patient factors. Thus, it helps in understanding the design modifications that will improve the quality of restoration and render good, efficient, long lasting restorations of prostheses to needy patients. Thank you.